All right, guys. Hey, what's up? Welcome back. We got projectile motion here. It's really just a continuation of what we were doing. So 13.4, motion in space continued, motion in space continued. And it's all about projectile motion here. And usually people think of like a cannon or a rocket or something being fired, some kind of missile being shot off from a single location, and it's not being acted on by any kind of like transverse force or magnetic fields or anything like that. So it's only really moving in two dimensions if you think about it. So if you have an XY coordinate system kind of like this, you have X, you have Y. And you start out, let's say you start out at the origin. You're not shooting this off at a cliff or anything like that. You're literally shooting it off right here. It could be like a golf ball going down the fairway or a soccer ball on, the field or something like that. Then you're shooting this thing off, this way. And eventually it's going to curve, do something like that. So this is your setup basically for your projectile. You have some initial angle. We'll call that angle alpha. So this angle here is alpha. And we could call it theta, it doesn't matter. And you have some initial speed, we'll call it V0. So, well, let me put it in green. So you have some initial speed V0. So V0 is the initial speed of the projectile, and then alpha is the launch angle, usually what it's called. So it's called the launch angle. And we're going to assume that the only force acting on this projectile is gravity. So there's no air resistance or anything like that, at least in our basic assumptions here. So we'll assume the only, we'll call it non-negligible force acting on the projectile is gravity. So Fg, force due to gravity, is going to be negative mg j hat. So that's going to be the only non-negligible force acting on this. And g here is the acceleration due to gravity. So g is the acceleration due to gravity. And you pick your favorite constant for that, whether you work in feet or meters or whatever. Probably on the exam I'll use 10 meters per second squared. It could be 32 feet per second squared. It just depends on what units you want to use and how precise you want to be with that constant. It could be 9.81. It just depends. But on the exam I'll use 10. Probably in homework or something like that, it'll probably want you to use 9.8 or 9.81. So G is 9.81 meters per second squared, or 32 feet per second squared. But on the exam, I'll probably round it to 10 if we use meters. So yeah, that's the only force acting on this object. And so the equation of motion, we want to find the position function. So the goal is to find r of t. So what do we know? We know from Newton's second law that forces, some of the forces in the y direction and the x direction, but the sum of the forces would be mass times acceleration. Well, we only have one force here. So we have mass times acceleration equals negative mg j hat. So naturally, the only acceleration we feel is negative g j hat. So that's the acceleration. Well, we need some initial conditions if we're going to go backwards. So velocity v of 0 is going to be v0 times a unit vector cosine alpha sine alpha. So that's the initial velocity. I know the initial speed is v0 multiplied by a unit vector in the direction of the launch angle, and we get the initial velocity. The initial position, we'll call it r of 0, is just the origin, because we're not launching it from some weird cliff or some height above the ground. We're assuming the launch height and the landing height are the same height. So it's basically 0. So now we have our acceleration. We need to find our position, or our velocity, and then our position. So the velocity is going to be the integral of a dt, which is going to be some constant c1 I hat minus, I should say minus g times t plus constant 2 j hat. So that's the velocity. And I use my initial velocity, v of 0 equals v0 cosine alpha, v0 sine alpha, and set that equal to, plug in t equals 0 for t, I get c1 comma c2. So then that tells me my velocity vector is going to be v0 cosine alpha comma v0 sine alpha minus g times t. So that is the velocity vector. Notice v0 cosine alpha, those are constants, right? v0 is a constant speed, like the initial speed, and alpha is the launch angle. So those two trig functions multiplied by v0, those are just numbers. Those are just constants. And that's going to be important when we integrate that to get the position function. So if I integrate that to get r of t, that's going to be integral v of t dt, which is going to be, well, v0 cosine alpha, that constant multiplied by t, plus a new constant, we'll call it w1, and then v0 cosine alpha, that constant, times t, minus gt squared over 2 plus w2. So that's my position function. And I can figure out the constants w1 and w2 using my initial condition, which I'm assuming is the origin based on the setup of the problem. So that's going to be 0, 0 equals, if I plug in t equals 0, I just get w1 comma w2. So actually there's no added constants w1 or w2. So my position function is v0 cosine alpha times t, and then v0, oh, that one should be sine, sorry, should be sine alpha right there, sine alpha times t minus g t squared over 2. So that is our position function as a function of time. So for t goes from 0 to t land, 0 less than t land, whenever it lands later. So that's something we actually want to find at some point. But here we can kind of see that x, we can have x component and y component of this position. So x is equal to v0 cosine alpha times t, which would mean that t we could write as x over v0 cosine alpha, and y would be equal to v0 sine alpha times t minus gt squared over 2. So actually, this would be, if I plug in t equals x over v cosine alpha, we'll get v0 sine alpha times x over cosine, or v0 cosine alpha minus g over 2 times x over v0 cosine alpha quantity squared. And I can simplify that a little bit. I can call it x times tangent of alpha. So there's a real world application of the tangent function, minus g over 2 times x over v0 squared secant squared alpha. So there's a real world application of secant. So this is actually just a parabola. So this is a parabola. This is the Cartesian equation of the parabola. Whoops, that should be an x squared right there. So the equation of motion is a parabola. So the equation of motion, or the position function, is a parabola. That's pretty cool. It's like a real world application of tangent and secant in the same thing. So we have a nice parabola. It's a nice shifted parabola. We already know it's shifted to the right a little bit and it's opening down. So that's what this finishes out as. It finishes out as a nice parabola here. So what are some calculations of interest? So calculations of interest. What might we want to know? First thing we might want to know is how far downfield does the projectile go? The second thing, well, actually let's try to answer each question before we move on to the next one. So how far downfield does the projectile go? Well, since it's a parabola, it's going to intersect the ground again at some point. So basically I set the y value equal to 0. So we set y equal to 0. And if I go back to, I guess I could try to factor that Cartesian equation, or I could use my vector function and solve for the time at which it lands. So if I set y equal to 0, I would get v0 sine alpha times t equals gt squared over 2. So I know there are two times at which y is equal to 0. T equals 0. Well, that's not of interest because we know we're already at the ground there. So I want to know what time later. So the t land, I'll call it, t land be equal to 2 over g times v0 sine alpha. So that's the time at which we land. And then if I want to know how far that is in the x direction, I just need to find x of t land. So x of t land will be v0 cosine alpha times t land, which is 2 over g v0 sine alpha, which we could say is 2 over g v0 squared. 2 sine times cosine, let me just write 1 over g then. 2 times sine times cosine is actually sine of 2 alpha. So that's how far downfield we go, and that's actually called the range. So this is called the range. Now there's two ways to increase the range: change the angle potentially, or change the initial speed. And you can increase the range. What's the maximum range, or what angle maximizes the range, basically? So that's a calculation of interest. What angle maximizes the range? So question 2, what angle maximizes the range? So the range, x range, we already know is 1 over g v0 squared times sine of 2 alpha. And let's say v0 is fixed and we're just changing the sign, basically. That's the only thing that could change. So basically the question is, what is the max value of sine 2 alpha? So the answer for this is sine of 2 alpha is maximized at 1. Well, that's when the angle 2 alpha is equal to pi over 2. Well, that's when alpha is equal to pi over 4. So that is the angle that maximizes your range for any given initial velocity. So we'll maximize range for any given velocity. So that's good to know. What else can we say? We say maybe how high does the, what is the vertical range? Could phrase it that way. What is the vertical range? What is the vertical range? So that's basically like the apex of the parabola, or the vertex of the parabola. So the answer, the vertex of the parabola occurs when y prime equals 0, right? No vertical velocity. So when your vertical velocity goes to 0, then you have no movement in the vertical direction up anymore. It's at 0, and then it's only going to go negative from that point. So if you set y prime equal to 0, y prime of t we know is v0 sine alpha minus g times t equals 0. So t max height is going to be v0 sine alpha over g. And so the vertical range is y of t max height. So basically plug that t value into the y component, so that'll be v0 sine alpha times t, which is v0 sine alpha over g, minus g over 2 times v0 sine alpha over g squared. And do some algebra, we get v0 sine squared alpha over g minus v0 squared, oh, that should be squared, v0 squared sine squared alpha over 2g. The g squared here cancels with the g out front, so that 2 in the denominator is the only thing left, and the g stays there. And we can combine that. That's like basically 1 minus a half is 1/2. So the answer here is v0 squared sine squared alpha over 2g. And that's the y range. So that's basically how high that's how high we're going to go. So the maximizing angle there would be pi over 2. I mean, that's obvious, right? Shoot it straight up and that's going to maximize the height that you get. You might say, what is the arc length? What is the distance traveled through the air? So that's number 4. what is the distance traveled through the air? So that might be, what is the parabola right here? Thanks. So what's the distance traveled through the parabola? It's like this curve here. At that point, we just want to find the arc length. So the answer is just the arc length. So the answer is just arc length. So you would integrate from 0 to t land the magnitude of r prime of t dt. So this would be the integral from 0 to t land, square root of v0 squared cosine squared alpha plus, and then v0 sine alpha minus gt quantity squared dt. And that integral is going to be probably pretty difficult. So difficult integral you might have to do some kind of trig substitution to do it. So that's going to be difficult. So we'll leave that to some kind of numerical integration technique probably. There's a way to do it by hand, I'm sure. Like I could work it out, trig substitution, but we'll just leave it alone. But that would be like the actual distance through the air that you travel, not just the x direction, not just the y direction, but the actual distance, the parabola, the actual arc length traveled through the air. So that would be a nice thing to compute. And then there's all kind of like, what initial angle do you need to achieve a certain range, and all kind of ways you could algebraically manipulate these formulas. So what angle was used if the range is a certain value. So basically you take your range equation and solve for the angle. So the range, we said the x range was 1 over g v0 squared sine 2 alpha, 1 over g v0 squared sine 2 alpha, and solve for alpha. So that's kind of the answer there. So yeah, that's kind of the gist of it all. There's only acceleration in the y direction, so there's no x acceleration. So note, throughout this whole discussion, there is no acceleration in the x direction. So let's check out an example. Let's give some time to catch up if you're writing all this down. Then we'll take a look at an example. Okay, so we got a pretty creative angle, or I'm sorry, a pretty creative example here. Example. It says a projectile is fired from a tank with initial speed of 400 meters per second. Find two angles of elevation or really that's just two launch angles that can be used to hit a target 3,000 meters away. 3 kilometers, that's a good distance. 3 kilometers is about like 2 miles. So 3K away. 3,200 kilometers, that would be 2 miles. So it's a good distance for this to hit. So that's assuming no air resistance. So this is very unlikely to be accurate. You're definitely going to slow down a lot with some air resistance, especially in Earth's atmosphere. So this is not a super realistic example, but we'll just play along to see what happens. So we got our setup. Let me just draw the XY coordinates. And we want to hit something 3,000 meters away. Let's say that's like right here. So x equals 3,000. And we have an initial speed of 400 meters per second. And we know the range is going to be 3,000. And that's going to be 1 over g times v0 squared times sine of 2 alpha. So basically I've got v0. All I need to get is alpha. And I'll use g as 9.81. And I'm going to need a calculator on this. So 3,000 equals 1 over 9.81 times 400 squared sine of 2 alpha. And so let's multiply by 9.81 and then divide by 400 squared. So 3,000 times 9.81 over 400 squared equals sine of 2 alpha. So let's get that number and then take the arc sine to get two angles. So 3,000 times 9.81 divided by 400 squared. I get that that is going to be 0.1839375 equals sine of 2 alpha. Let me make sure my mode's in the right. I'll do degrees, sure. So let me take the arc sine of that. So alpha 1, or 2 times alpha 1 will be arc sine of 0.8 or 183975. So let me do shift sine of that, and I'm going to get this in degrees, so that's like 10.599 degrees if I round it there. So alpha 1, divide that thing by 2, I get 5.2996 degrees. So 5.2996 degrees. So that's the first angle. I could make it like a super low angle, and that would hit my target, right? It could be like this super low parabola, like that, 5 degrees off the vertical. So that's the first angle I could use. Or I could say 2 times alpha 2 would be 180 minus alpha 1. Whoops, I could just say alpha 2 would be, actually I should be careful. Should I care about this? I don't think so. Having a little brain fart. So I'm just going to say 2 times alpha 2 would be 180 minus 10.599 Yeah, I should have been careful. So this is going to be, so the other angle would be, let's see, 180 minus 10.599 would be 169.401 degrees. And divide that by 2, I get alpha 2 is going to be, so divide that by 2, 84.7005 degrees. So I guess I could have just done 90 minus the previous, but that would be something closer to vertical, and that will also hit the target. So it's alpha 2, and it's alpha 1. So that will also hit the target 3,000 meters away. So I like that problem. That's a really cool one. Just makes you think a little bit about what you could do. Again, air resistance is not being taken into account. That's greatly going to affect the results of the projectile motion equation. So you have to take that into account in your initial model. Also, any other crazy stuff that could happen. But yeah, like Coriolis forces, those come into effect really whenever you're like doing long range stuff. So Coriolis forces, like that's because the Earth is spinning itself. And so your projectile may deviate from a straight line a little bit because of the rotation of the Earth. So a lot of these things have to be taken into account when you're doing real projectile motion equations. But for this basic stuff that we're doing, we just stick to only force due to gravity acting on the object. So anyway, that's it for today. Have a good one. Talk to you later. Bye.